In this video, we are going to discuss the orbital wave functions and radial shape of orbitals. Orbital is the region around the nucleus where the probability of finding electron is maximum, and according to wave mechanics, orbitals are described by orbital wave function. Orbital wave function, it is the product of radial wave function, which is related to the size of orbital, and the angular wave function, which describes the shape of orbital. For S orbital, the angular dependence is not there, and therefore it is a spherically symmetrical, whereas P, D and F orbitals have angular dependence, and therefore these are directional. P orbital is dumbbell shape, D orbital is double dumbbell shape, F orbital has a three-dimensional complicated structure. The radial dependence of an orbital, it is represented by plotting a graph between radial wave function and the distance from the nucleus, that is r, and this is the formula for radial wave function. It is equal to z upon a0 raised to 3 by 2 into e raised to minus 2r by a0. For 1s orbital, when radial wave function or psi square is plotted versus r, that is distance from the nucleus, then this is the nature of graph. And for 1s orbital, as per this formula, that is n minus l minus 1, number of nodes equal to n minus l minus 1. Actually for 1s orbital, principal quantum number is 1, azimuthal quantum number is 0. So 1 minus 0 minus 1, that is equal to 0 nodes. And you know, nodes, it is a region around the nucleus where there is a less probability of finding electron. So for 1s orbital, number of nodes are equal to 0. There is no any node. And radial wave function of 1s orbital does not pass through 0. Hence 1s orbital has no radial node, and the point at which radial wave function is 0, it is called as node. So for 1s orbital, node is not there. Now consider the 2s orbital. For 2s orbital, when we plot the radial wave function versus distance from the nucleus in angstrom, then this is the nature of graph, and this line crosses x-axis at a certain point, and this is the node. So here number of nodes again n minus l minus 1, n is 2 for 2s orbital, principal quantum number is 2, azimuthal quantum number is 0. So 2 minus 0 minus 1, that is equal to 1 node, and therefore for 2s orbital there is a 1 node, and this point at which this line crosses the x-axis, this is the node of 2s orbital. For 3s orbital, again when radial wave function is plotted versus distance from the nucleus, then this is the nature of graph. So this line crosses x-axis at 2 points. These are the nodes. So number of nodes n minus l minus 1 for 3s orbital, n is equal to 3, l is equal to 0. So 3 minus 0 minus 1, that is equal to 2 nodes, and these 2 points at which this graph cross the x-axis, these are the 2 nodes. These are the 2 nodes of 3s orbital. Now next point is radial probability distribution curves. The radial probability distribution curves of electron gives the probability of finding electron at different radial distance from the nucleus, and it is the plot of distribution function d, that is 4 pi r square psi square versus distance from the nucleus, that is r. and it shows the distribution of electron density as a function of distance from the nucleus. In this probability curve, there are certain maxima and minima. The maximum in the curve indicates the distance from the nucleus where there is a highest probability of finding electron or electronic density or electronic cloud, that is the orbital. And the minimum in the curve indicates the lowest density, electron density or node, or less probability of finding electron, that is the node. Now consider the 1s orbital. So probability distribution curve for 1s orbital. So here for 1s orbital, when distribution function d, that is 4 pi r square psi square, is plotted versus distance from the nucleus, then this is the nature of graph. So suppose when distance from the nucleus is 0, then probability of finding electron is 0, and as we go away from the nucleus, the probability of finding electron increases, and at a certain distance there is a maximum probability of finding electron. And for 1s orbital, this distance is 0.529. At 0.529 angstrom, there is a maximum probability of finding electron, and this is the radius of 1s orbital. Now from this distance, again when we go away from the nucleus, then probability of finding electron decreases. So this is for 1s orbital, and again this line or distribution function, it is not equal to 0 at any point, and therefore for 1s orbital there is no any node, radial node. Now consider nucleus. This is the nucleus, and this is the 1s orbital. You know, electrons are revolving around the nucleus, and this is the 1s orbital, electronic cloud, which is spherically symmetrical, and there is a maximum probability of finding electron at 0.529 angstrom, and this is the radius of 1s orbital. Now consider the radial probability distribution curve for 2s orbital. Again, when distribution function d is plotted versus the distance from the nucleus, then the nature of graph is like this. There are two maxima. This is one maximum and this is another maximum, and at the same time there is a one minima or minimum. So this first maximum, it is the electron density or probability of finding electron is maximum at 0.529 angstrom, and this is corresponds to radius of 1s orbital. And second maximum, it is corresponds to the radius of 2s orbital, and radius of 2s orbital is found to be 5 into 0.529 angstrom. This is for 2s orbital, and this minimum, it indicates the node or radial node of 2s orbital. For 2s orbital there is one radial node. Again, this is the 2s orbital, and distance from the nucleus up to this 2s orbital, it is 5 into 0.529 angstrom, and this is the radius of 2s orbital. Obviously radius of 2s orbital is greater than the radius of 1s orbital. Now consider the radial probability distribution curve for 3s orbital. Again, when distribution function is plotted versus the distance from the nucleus, that is r in angstrom, then this is the nature of curve or graph for 3s orbital. So first maximum it is for 1s orbital, second maximum or second peak it is for 2s orbital, and this third maximum it is for 3s orbital. So 1s, 2s and 3s. So this is for 3s orbital, and here you can see there are 3 maxima corresponding to 1s, 2s and 3s orbitals respectively. At the same time there are 2 minima. One minimum is in between 1s and 2s orbital, that is for one node, and another minimum it is in between 2s and 3s orbital, this is for another node. So for 3s orbital there are 2 nodes, radial nodes. So in this way the radial probability distribution curve for 1s orbital, that is for hydrogen atom, shows a maxima which corresponds to radius of 1s orbital, and radius of 1s orbital is 0.529 angstrom. The radial probability distribution curve for 2s orbital shows 2 maxima. One is for 1s orbital and second is for 2s orbital. In between 2 maxima there is a 1 minima or minimum where there is a less probability of finding electron. This is called as nodal point or the radial node, and the radial probability distribution curve for 3s orbital shows 3 maxima corresponding to 1s orbital, 2s orbital and 3s orbital, and in this radial probability distribution curve of 3s orbital there are 2 minima corresponding to 2 nodal points. And this is about the orbital wave functions and radial shape of orbitals. So in this way here we completed the atomic structure. Now serially go through all the videos, listen, or regularly you watch all the videos, make a notes and have a good study. All the best.